The organizers that invited me here on this seminar, I would like to speak about the joint work with Ivan Soskov and Stefan Butev from Sofia University. The idea is to define and to consider a relation between two structures which concern the definability in both structures. So I shall start with some motivation from degree spectra, and after that I shall set exactly what I mean about the definable sets in the structure. And after considering these conservative k-n extensions, the idea is the sigma k definable sets in the first structures to be sigma n definable in the second. One of the example will be 1-0 extension will be the jump of a structure, and we will consider another example which is 0-1 extension, which is something like jumping birth of a structure. So let A be a countable structure of relational type. Enumeration we consider by enumeration we mean every one-to-one mapping of the natural numbers to the structure. By this symbol we shall denote the representation of a set under the enumeration F, and here is the presentation of the structure under the enumeration is the join of all presentation of the predicates and equality. The notion of the degree spectra is introduced by Linda Richter, and is the set of all Turing degrees of the presentation of the structure. I shall concentrate about two results which we made in 2008 together with Soskov. The first one is that every first jump spectrum is a spectrum of a structure. Of course, I forgot to say what is the jump spectrum. The n-jump spectrum is the n jumps of all elements of the spectrum, and we shall use the very nice property that Knife proved, that for every automorphically non-trivial structure, the n-jump spectrum is a closed set of degrees, which means that whenever Turing degree is in the n-jump spectrum, the whole upper cone is subset of the spectrum. And the results are first, for every structure, we can find a structure B such that the degree spectrum of B is exactly the first jump spectrum of the first structure, and the second result is something like the jump inversion theorem. If we have a complex enough structure A, here the degree spectrum of A to be a subset of the jump spectrum of another structure C, we can construct a structure B with the first jump spectrum exactly the degree spectrum of E, the original structure, and moreover the degree spectrum of B subset of C. So the degree spectrum is a measure of complexity of the structure, but is not enough precise from the point of view of definability. We shall see very simple examples of structures with the same spectrum, but with different expressive power. So I shall start with definability. Computable sigma n formulas is exactly like the infinitary sigma n formulas, but with computably enumerable disjunctions. So here is the definition. Sigma 0-1 computable formulas are finitely quantified free formulas, and sigma n plus 1 computable formula is disjunction, computably enumerable disjunctions, a formula of the this kind existential formula, where here psi is a finite conjunction of sigma n and p and computably formulas. And n plus 1 formulas are the negations of sigma, computably sigma n plus 1 formulas. A set is called formally sigma n definable if there exists a computable sigma n formula and finitely many parameters from the domain T1, Tr, so that this equivalence holds. There is a nice characterization of definable sets, formally definable sets, and by external notion using enumerations, a subset is said to be a subset of the domain of the structure is relatively intrinsically sigma 0 n plus 1 in A if for every enumeration of the structure the presentation of the set is sigma 0 n plus 1 relative to the presentation of the structure, or equivalently the presentation of the set X is Ca relative to the n jump of the presentation of the structure. And the result of Ashnight, Manasseh, Lemon, and Chisholm shows that a set is relatively sigma 0 n in A if and only if X is formally sigma n definable on N. So we shall use this result to introduce our notion, but first let me see an example. Consider a very simple structure, the empty structure, and the structure of the natural numbers with we add a graph of successor functions. It's obvious that they have the same degree spectrum, but the definable sigma 1 definable sets over the first structure are all finite and cofinite sets. But in the second structure, the sigma 1 definable sets are all C sets. So it's clear that the second structure is more has more expressive power than the first one. So to doing this, to represent this relation, we will extend first the definition of the enumeration of a structure. Enumeration we shall call a tuple pair of one-to-one mapping again from the set of natural numbers onto the domain of structure, and R alpha is a subset of the natural numbers, but such that the representation of the structure A is computable in R alpha. We denote this by this symbol. Alpha is enumeration of A. If you consider R alpha here to be exactly the presentation, this presentation of the structure on the F alpha, we will receive the previous definition. And this is another notation, the n jump of alpha, we shall denote for every alpha enumeration of the structure A, F alpha the same mapping, and the n jump of R alpha. So we will compare two enumerations. Let alpha enumeration of the structure A and beta on the structure B. We say that alpha is less than or equal to beta if R alpha is computable in R beta, and moreover the set of all xy which are going by F alpha and beta the same element is Cn and R beta. So now consider two structures A and B such that the domain of A, the first one, is a subset of the domain of the second. The first relation, Kn are natural numbers, A is less than Kn on B if for every enumeration beta of B there exists enumeration alpha of U such that the K jump of alpha is less than the N jump of beta. And the second relation on the opposite directions says that holds whenever for every enumeration alpha of A there exists enumeration beta of B such that the n jump of beta is less than the k jump of alpha. So we said that B is Kn conservative extension of A if both relations hold, and know that this is not symmetric. The first property is that if we have the first relations, then the n-Jump spectrum of B is a subset of the k-Jump spectrum of A. The second is the opposite, and when B is Kn conservative extension of A, then the k-Jump spectrum of A is exactly the n-Jump spectrum of B. But the opposite direction is not true. We have even more here from the point of definability. If the first relation holds, this one, then every k plus 1, sigma k plus 1 set definable in A, of course subset of the domain of the first structure A, is n plus 1 definable, sigma n plus 1 definable on B. Here we have the opposite, and when B is Kn conservative extension of A, then every k plus 1, sigma k plus 1 definable sets of n exactly coincide with the n plus 1, sigma n plus 1 definable on beta. The opposite direction is not always true. We can see a very simple example. Consider the empty structure with a countable set A. Again, the sigma n definable sets here are only the finite and cofinite set, and this is for every n. So we have this implication holds, but the other, this is not possible, because if you consider an effective enumeration of A, there is no enumeration again of OA, which n-Jump is below A. Because of this, one solution is to extend, to get a more stronger condition for the opposite direction. We shall use the Muskovakis extension. Muskovakis used this defining prime compatibility and search compatibility, and we get a new element and a pairing function such that none of the elements of A is a pair, and close A0 under these pairing functions. We have the decoding functions L and R, and the Muskovakis extension of the structure A we called A star with the initial predicates with this extension. A0 is a new unary predicate and a graph of pair L and L. It happens that A star is Nn for every n conservative extension of A, and moreover, if B is Kn conservative extension of A, then B star is also K conservative extension of A. Here we can formulate the opposite condition. If you have two structures such that the second one, the domain, contains the whole A star, and if you know for the subset of A star that every k plus 1 definable on A star is sigma n plus 1 definable on B, then we can claim that this relation holds. So we have the complete characterization from the point of view of but this extension of Muskovakis. Okay, now I'm going to give two examples for these relations with K1 and N0, and after that the opposite. The first one, to define the jump of a structure, I need the forcing relations for every n. We define a forcing relation for forces n here, so that we can define the jump actually of the structure. Here W is the CA set with index E. Here tau, finite part, we mean finite mappings from n onto A. And I just only mentioned that here, when the computation goes on and asks something from the oracle for an element which is outside the domain of tau, the computation is undefined, doesn't answer. So the other things here, DV is the canonical, the finite set with canonical code V. Here is the computable enumerable set with code V. And having these forcing relations, we define in A star a predicate which is analog, in case when n is 0, analog of the Kliment set of triple finite part E and X, such that there exists a finite part tau which extend delta, the tau enforces the formula Fex. Actually, this set is, one can think that this is some kind of universal for all sigma n plus 1 definable sets on the structure A star. So it's sigma n plus 1 definable, and it's not sigma n definable. So the jump we define the following way. We get the A star, the extension of A. We put this predicate Kn, and this we call the jump of the structure N. So the jump of the structure A is N0 conservative extension of A. About the relation 0, 0, we have that we receive strongly increasing sequence of A, the first jump of A, the second, and so on. And we have also the property that every sigma 2 definable set in the n jump of A is sigma 1 in the n plus first jump. Also, we have agreement with the n jump spectrum. The n jump spectrum of the structure A is exactly the degree spectrum of n jump of A. So, for the second example, for the opposite relation, which is 0, 1, we shall define 0, 1 conservative extension of A for complex enough structures which degree spectrum contains only elements which are about 0 prime. And this we will do using marker extension. Marker introduce this characterization, this method, proving that for every n there is a alpha 0 categorical, almost strongly minimal theory, which is not sigma n axiomatizable. After that, Goncharov and Tusinov consider the general case, marker do only for some special structures as graphs and others. They extend the notion of marker extension for the general case. They prove also some effective model or theoretical result, and is the following. We get the structure. For every predicate, we add a new set of witnesses. Every element of this set witness that the predicate is true over this tuple. So we extend each predicate with another argument so that he is true over, on this case, with this exactly unique x. X is, of course, connected with the other elements, A's. And we have this property: if there exists an x in X where the extended predicate is true, the original predicate is also true. So this is the first step. We add this new, there exists fellow for every predicate. We add that to the domain. We replace the original predicates with this, and we add also as unique predicates for every unary predicates for every predicate a new one. The second step is to do this of the received structure with the negations of the predicates. For every predicate of the structure A there exists, we add a unique element which says that the predicate is not true over this couple. So we call this set for every fellow, and we have this property. We extend again the predicate to satisfy this equivalence, and we have this property that for every y of y, if p is true over these tuples, then p exists, there exists is also true. So finally, the wishing predicates, the wishing property is the following: each of the initial predicate is true if there exists an x from x for every y and y. This predicate is true. So we add these fellows as new elements, new unary predicates, and the good thing is that this construction does not concern enumerations, and everything is absolutely strict model theoretic construction. So we have this property that the received structure is 0-1 conservative extension of A, if A is complex enough, which means that the first jump of this structure is 0-0 conservative extension of A. So for every complex enough structure, which elements of the degree spectrum are above 0 to the k, we have this. We have that for each natural numbers, we can find a structure B such that this equivalence holds. I would like to mention that in 2009, two notions of jump of a structure appears. The first one is of Antonio Montalban. He uses a different approach. He does not extend the domain, but he added a complete set of Pn predicates to the structure, and this the received structure he called the jump of a structure. He has absolutely the same property that sigma 2 definable sets in the original structure are sigma 1 definable of the jump. And there is another notion of Stukachev, Alexei Stukachev, who introduced the jump of a structure for sigma reducibility. He extends hereditarily finite superstructure. He get this, and he had satisfaction relations on it. He proves also the large inversion theorem for the sigma reducibilities. So again, using marker extensions. But I think that the three notions are almost equivalent. There are some difference. For example, for Antonio Montalban and assuming existence of zero sharp, and Vadim Pluzarenko independently prove that there exists a structure with jump is equivalent to the structure. So the jump from the point of view of sigma reducibility has a fixed point. Our notion is not has not this. The jumps are strongly increased. So we would like to find appropriate relations, and I think that the three jumps are absolutely equivalent from the point of view of definability of the structure. So if you drop this, I think if you drop this condition, probably the three jumps will be equivalent. And moreover, there are some other problems here. We would like to relativize the jump inversion theorem and to formulate these whole things for arbitrary constructive ordinals. So thank you.
Thank you, Alexandra, for your talk. Are there any questions? Well, okay, I guess that means everything was clear enough. So let's thank the speaker again.